Viewers, welcome back to the channel Maths with Berlin. So today here we are with another part of the rare theory series. So basically in this series we cover various topics that can be asked in JEE Advanced, the theory part of it, and we try to solve some basic problems along with the theory. So let's start without any ado. So we have got today a log concave series, right? This is a very important topic if you consider the JEE Advanced perspective or even the Olympiad perspective. So in this series what we cover is, let me just give you a brief idea. We all have seen this kind of an expression, right, that ai squared is greater than equal to ai plus 1 ai minus 1, or basically if you, some of us have also seen this in this following format, that is ai over ai plus 1 is greater than or equal to ai minus 1 over ai, right? So this is how we have always seen it, that the ratio increases. If you see, right, the ratio is increasing. Now this is a very important series when you talk about higher mathematics. So let's just start. So what I have written is the sequence, let there be a sequence of ai for i belongs to natural numbers such that ai, wait a minute, it's just an overwriting, yeah, ai is greater than less than a2, that is less than a3, and so on, so up to ak, right? And after that it reverses, like ak is greater than ak1, ak plus 2, ak plus 3, and up to an, right? So what we can say is that there is a maxima of the sequence, right? That is what we want. We don't want anything else, we just want the maxima to exist, right? Like this, there must be a maxima, right? So that's our need for log concave series. Now this sequence is not only called a log concave series, this sequence is also called as the unimodal series, right? This is called as a unimodal series. Now the basic example of this is the binomial term, right? Now you can understand where this is going, right? We are trying to use this series into a binomial question, right? Just wait and watch. So now we also call this as the LC series, right? Not to doubt that this is not the physics LC graphs. This is just the log concave series. So what we have done is that for log concave series we have to be following the following expression that I have already shown you in the shown you here, right? This one, you have to just follow this part. Now then that series is called as the log concave series or even the LC series, right? Now why do we actually see what is the basis of log concave series? Now log concave series has a log in it, so just try to apply the logarithm and you would get basically an am that is greater than less than, am is less than the number that is so let's say the number n, so that's n, right? The am of previous and the successor, right? You can understand what I have written, successor is basically less than the number that is there in the between, right? Logarithm of the number that is there in the between. Now, so why do we actually need to express in the terms of logarithm is basically that geometric sequences or even ratios are very difficult to deal with in comparison to addition and subtraction, right? So there is another thing that is ultra log concave series, right? We discuss another thing that is ultra log concave series before going into the problem. So in ultra log concave series, what we tell is if a sequence is ultra log concave, then it is also log concave, right? Like being ultra log concave, that is ULC, being ULC directly implies that the series is an LC, right? I am using the short terms, that is UC, ULC and LC. So I think that's pretty enough of an explanation. And now, so the condition for ultra log concave series is basically that the binomial term is in the division, in the denominator of the log concave series. You just divide the binomial terms of each, right? You can just check it out on your own. I will be not reading it out because it's very difficult to read it out, right? So finally, when you simplify this expression, what comes out to be very useful is ai squared is greater than or equal to ai plus 1 into ai minus 1 times 1 plus 1 by ai times 1 plus 1 by n minus I. So this is the condition basically. Now moving on, so this is our main problem for today, right? This is the main problem where it starts. So just try to focus it on this part right now. So it is given to us that Newton's theorem. What is Newton's theorem? Is Newton said that if p of x is a real coefficient, right? If it is a real coefficient and real rooted function, right? Let me just write it down so that it's easy for you to understand. It's a real coefficient and real rooted, right? Both of the conditions must satisfy. Real rooted function is there, function. It must also be a function p of x, right? If p of x satisfies that real rooted condition and also the real coefficient condition, and also it is a function, then we can say that the terms bj, right? If you just represent the terms as the follows, let me just show you. So if you just represent the terms as ncj times bj, right, the coefficient, if you just represent it like this, then bj is an LC series, right? Now if you understand what I have taught till now, you would directly claim to me that ncj is already an ULC, right? Wait a minute, just it's a ULC. bj, I just told that it is an LC, but if you check it, it will be an ULC for most of the cases, not always, but in most of the cases it is an ULC. And if one of them is an ULC, you can directly say that it is an ULC. So basically, if equivalently, what I have written is equivalently p of x, if it can be represented as aj times x to the power j, it's just a normal representation of a function. Aj can also be 0, not a difficult thing to write about. Then the coefficients are always an ULC, right? That is ultra log concave. They are ultra log concave. Now why is it concave? It is because that the graph is like this, right? Why do we call it a concave graph? So you know this is a concave graph, right? That is, you get a maxima at some point, right? You get this maxima. So that's the reason for calling it a concave graph. Now, so do we need to prove this statement, right? We will prove this statement, that is, if px can be represented as the follows, then and px is a real rooted function, then the coefficients are an ultra log concave sequence, right? Now, so what you do is you try to understand the value of p dash x, right? You know the Rolle's theorem, right? Rolle's theorem. So Rolle's theorem states that if p of x has a root in between a and b, then p dash x must have a root in c that is in between a and b, right? That is what Rolle's theorem says to us. Now, so basically applying the Rolle's theorem, we can get the following first fact that is there, fact number 1. So let me just rub it so that you can understand which is the main part that we are talking about. So there's a lot of things written on the board. So yeah, now it's a bit clear, I think so. So p dash x has n minus 1 roots, and r of x, if you write r of x as x to the power n times p of 1 by x, then you can state that it is just nothing but this expression. Just try to formulate it on your own and you will get it, right? Now if you see, r of x is also a real rooted function basically, right? R of x is also a real rooted function. So what you do is you try to apply differentiation to the kth term in p of x. When you apply the differentiation to the kth term, try to formulate it and you will just get the expression to be this. For now you may just try to understand this as a fact that when you differentiate a polynomial to the k minus 1th term, you get the following expression, that is j factorial by k minus 1 factorial, although it is not very difficult to prove, but yeah. So what you do is, after this, is that you can represent Rx as q into 1 by x. This Rx is not based, so wait a minute, let me just clarify. So this is a different Rx and this is a different Rx. We are not claiming this two as same, right? This was just the facts, end it here, right? It's over here. After that you get the proof. The proof is a different story altogether, right? Now Rx is a real rooted function, obviously, as stated in the fact, right? Now when you differentiate R of x, right, you write R of x in the following terms and then you differentiate it to the n minus 1 plus k, n minus k plus 1 term. When you differentiate this R of x, it just becomes a quadratic. A bit surprising, right? Yeah, so it becomes a quadratic, and now this has also real roots, because differentiation does not change the nature of the roots. Like if there is a real rooted function and you differentiate it, you will obviously get a real rooted function again. Now therefore what you do is, you put the discriminant is greater than or equal to 0, and then after you get that the value of this as follows, and hence it can also be represented as like this. Now you might be wondering about how can this be useful. Is basically, there can be a question where you are being asked in, like in JEE mains most probably, or in JEE mains obviously. So what you can do is, you are given the following function, right? Let's say you are given this following function and you are asked to find the number of real roots of the following function. So now what you can do is, you can just try to use this fact, that is the 4 square must be greater than or equal to, like, 2 squared must be greater than or equal to 1 into 1. Also 1 squared, right? If I take this as the middle term, then 2 squared. If I take this as the middle term, right, if I take this one as the middle term, then 1 square must be greater than or equal to 2 into 1. But that is a false statement. Therefore this has less than 3 real roots. Less than 3 real roots. Now less than 3 might be how much? Can it be 1? Yeah. Can it be 2? No. Right? So the story of 2 is not there. Now it's easy, because either it is 1 real root, 0 real roots cannot be there, so therefore it must be 1 real root, right? So it's very interesting and very useful if you know how to use this mathematics, right? So that's it for today, I suppose so, and thank you everyone for attending the class. Yeah.